Hello students, in this video we will study a new concept, a new topic, that is equipotential surfaces. We will define the equipotential surface and we will try to write some properties of equipotential surface. Then we will try to draw the equipotential surfaces for different configuration of charges. Okay. First let us define it. What is equipotential surface? As the name of this surface only itself indicates, itself shows that it is equipotential surface. That means it is a surface. Suppose for example, if I draw a surface here, generally of any shape, this is a surface. If on this surface, if we take any point, if potential at every point of this surface is same, potential at every point of this surface is same, then it is called as equipotential surface. That means potential at all the points are equal. This surface is known as equipotential surface. So what is equipotential surface? The surface on which potential at every point is same. This is called as the surface on which potential at every point is same. That surface is called as equipotential surface. Then suppose if I consider a equipotential surface like this. If I take 2 points on the equipotential surface, this is A, this is B. These are the 2 points. The definition, suppose if I have a test charge here, a test charge, and I want to move it from A to B. I want to move it from A to B. How much work is done? The definition of work, it says that W is equal to the charge that we are moving multiplied by potential difference between A and B. Should be VB minus VA. That we studied in last class, last video. What is work done? Charge multiplied by potential difference between these 2 points. But definition of equipotential surface. Equipotential surface says that at these 2 points potential is same. That means VB is equal to VA. Take any other point also, that will be same. Because equipotential surface says that at these 2 points potentials are equal. That means VB is equal to VA. If VB is equal to VA, then what will be the potential difference between these 2 points? Potential difference between these 2 points is 0 because both are equal. Then work definition says that work is equal to charge that we are moving multiplied by potential difference. If potential difference comes to be 0, then what is work done? Work done should be 0. That means work done is equal to 0. That means on an equipotential surface, if you move any charge from one point to other point, if you take any 2 points, potential difference between those 2 points will be 0. Then what is work done in moving a charge from one point to other point on the equipotential surface? That should be 0 because there is no potential difference. First point you should remember. Let us say first property, that property number 1. What is that property? Is work done in moving a charge, from one point to another, on an equipotential surface, that work done is 0, because we don't have any potential difference between 2 points. Then work done will be 0. Suppose this is second point. Remember, on the equipotential surface, if I have a test positive charge and I will move it like this through a distance dl. How much distance? dl distance. I know that there is no potential difference. If an electric field exists here, then how much force I have to apply to move the charge? Suppose if this is a positive charge electric field and this is a point A, this is point B. If I suppose that there is electric field direction is this, let us suppose this point is A, this point is B. I want to move the test positive charge from A to B. Here exists an electric field E. If I am moving this charge through a distance dl, which is in the plane of equipotential surface, then what is the work done formula? Work done is equal to what is the force that I am applying multiplied by what? Dx, multiplied by dl or dl. What is the force formula? Force is Q naught into E into dl. Okay, this is work done, Q naught into E into dl. If I take W is equal to 0, work done is 0 from the first point we studied. If W is equal to 0 means this will be 0. That means E dot dl, this will be moved in the direction, will take cos theta. Actually formula is F dl cos theta. That means I can take this right like this. What is formula? This will be F into dl into cos theta. If I say this is Q naught into E into dl cos theta, we know that work done comes to be 0. Work done is 0. Work done is 0 means what? Q naught into E into dl cos theta is equal to 0. Okay. Work done is 0 means cos theta must be 0. Cos theta is 0 means what should be theta? That means, which implies that if I remove this scalar quantity, I say that E dot dl, E dl cos theta means E dot dl. E dot dl is equal to 0. Dot product of two vectors is 0, which implies that, see, EDL is equal to 0, EDL cos theta is equal to 0 means cos theta is equal to 0. Cos theta is equal to 0 means theta is equal to 90. A dot B is equal to, if two vectors dot product is 0, it means that A is perpendicular to B. That means E is perpendicular to DL. E is perpendicular to DL. DL is in the plane of equipotential surface. E is perpendicular to DL means, suppose this is the equipotential surface. This is DL. I am saying that DL is perpendicular to equipotential. This is DL. DL is in the plane of equipotential surface and electric field is perpendicular to DL. That means if this is the electric equipotential surface, then electric field will be like this. DL is in the plane of equipotential surface. Electric field is perpendicular to this means what? Electric field is like this. That means this is equipotential surface, electric field is like this. So, if work done is 0, then it gives me a conclusion that electric field is always perpendicular to equipotential surface. Our equipotential surface will be always perpendicular to the electric field direction. Or, from this what we can decide is, see, for any type of configuration, for any configuration of charge. It may be point charge, it may be system of charge, it may be dipole. For any configuration of charge, equipotential surface through a point, equipotential surface through a point will be always perpendicular to the direction of electric field. Equipotential surface through any point. Suppose if this is the direction of electric field, I want to draw equipotential surface through this point. That means I want to draw a surface which is passing through these points. If electric field direction is like this, if this is the direction of electric field, this is the direction of electric field, then equipotential surface must be perpendicular to electric field. This is the direction of electric field, then this surface should be like this, through any point. Through this point perpendicular to the field, through this point perpendicular to the field. It means equipotential surface will be always perpendicular to the direction of field. This is field direction, this is equipotential surface. Okay, make a note of this. That means if we know the direction of electric field, we can draw the equipotential surface through any point, because we know that equipotential surface is perpendicular to the field. Or if we have a equipotential surface for a given configuration of charge, suppose this is a charge, point charge. I say that these are equipotential surfaces. How to draw the field? We know that field is perpendicular to equipotential surface. That means this should be the direction of the field. That means if we know the direction of the field, you can draw equipotential surface. Or if we know the orientation or how equipotential surfaces are drawn, if you draw a line which is perpendicular to equipotential surface, then this line will give me the direction of electric field. That means depending on the equipotential surface, you can draw the electric field, or you can say the direction of electric field. Equipotential surface through any point shows or gives an idea of direction of the field. How? Equipotential surface we know means if we draw a line perpendicular to the equipotential surface, that gives me the direction of electric field. And the property number 4 is equipotential surfaces or two equipotential surfaces. We can write two equipotential surfaces never intersect each other, because it gives the direction of the electric field. Means if two electric equipotential surfaces if suppose that this is the equipotential surface, what is the direction of electric field? This. If another equipotential surface intersect with this at this point, then at this point we have another direction for equipotential electric field. See, according to this surface, it is perpendicular to this. According to this surface, electric field is perpendicular. That means if they intersect at a particular point, what it indicates is at this particular point, electric field has two directions. One vector having two directions at a point is not possible. That means if electric field lines, equipotential surface, like electric field lines, equipotential surfaces never intersect. If they intersect at a point, it means that while drawing only, we do not intersect the two lines, because two surfaces. Because if they intersect, it means that at the point of intersection, electric field has two directions, which is not possible. See, for any configuration of charge, if you are drawing equipotential surface, we don't intersect two equipotential surfaces at a particular point. If they intersect, what happens? At this point, electric field will be having two directions. One vector at a point having two directions is not possible. Therefore, intersection is also not possible. Okay? Two equipotential surfaces never intersect each other. Then another property we'll study. Equipotential surfaces are more closer. This property is very important. In drawing the equipotential surface, this property is very more closer to each other. In the region of, or in the region of strong field, and they are further apart. That means they are away from each other. Further apart in the region of weak fields. That means if equipotential surfaces are closer to each other, then it indicates the field is strong in that region. If the equipotential surfaces are away from each other, then the field is weak in that region. Suppose if I draw a equipotential surface for a particular charge, see, suppose for example this is positive charge. If I am drawing the equipotential surfaces like this, then I will draw them like this. When I am close to the charge, equipotential surfaces are closer to each other. When I move away from the charge, equipotential surfaces are further apart. They are away from each other. This indicates that in this region electric field is strong, in this region electric field is weak. Okay? So equipotential surfaces also indicate the strength of electric field. Okay? Write down these properties. Okay. These are few important properties. Then we'll see how to draw the equipotential surfaces for different charges. Okay? Drawing of equipotential surfaces. Okay? Now see, first we'll draw for point charge. Isolated point charge. If it is a point charge like this, suppose that if it is positive charge, let us suppose it is positive charge, then we know how to draw the electric field lines. These are the electric field lines going away from the positive charge. Then if I want to draw the equipotential surface for this, then what I will do? Suppose, see, what is V? V is equal to 1 by 4 pi epsilon naught. If this charge is Q, then V is nothing but 1 by 4 pi epsilon naught Q by R. See, if charge I have fixed, I have a charge Q. Around this charge I want to draw a equipotential surface. It means I want to draw a surface by selecting some points of equal potential. Suppose if I select one point here which is at distance R, one point here which is at distance R. It means I am selecting those points which are at the same distance. See, Q is already constant. Q is fixed. If I select those points which are at the same distance, R, all the points are at the same distance. That means for all points, this is the distance R, potential is 1 by 4 pi epsilon Q by R. At this point also same potential. At this point also same potential. That means around this charge I have selected so many points which are having same potential. That means if I draw a surface covering all those points, this surface gives me equipotential. See, for equipotential surface Q is already constant. I should fix R. R is same for all the charges. That means equipotential surface will be a sphere. Suppose if it is spherical charge, spherically, then equipotential surface will be a sphere covering all this, not circle. Okay, it is two-dimensional board. Then you can, these are the spheres. Then again, if I select some points which are at this equal distance from this charge, I can draw one more line like this, one more surface like this. This is also equipotential surface. Then if I take one at a distance R, all points at distances R, then I can draw one more line like, one more surface like this. This is also equipotential surface. I can draw one more surface like this. This is also equipotential surface because all the points have same potential because they are at the same distance from this charge. Okay, I can draw one more surface like this. All concentric spheres I have drawn. See, what property number 5 I have written here while writing the properties. Property number 5 I have written. What in that property what we studied? Electric field lines indicate the strength of electric field. Equipotential surface indicate the strength of electric field. See, these equipotential surfaces are closer to each other. When we are close to the charge, when we are near the charge, equipotential surfaces are closer. When I move away from the charge, equipotential surfaces are becoming away from each other. That means here the equipotential surfaces are closer, which indicates that closer to the charge we have strong field and away from the charge field goes on becoming weak, because we know that field is equal to 1 by 4 pi epsilon naught Q by R square. As the distance increases, field decreases. As the field decreases, in the weaker field regions, equipotential surfaces will be away from each other. This closer distance between these surfaces indicate that field is strong here, strong field region, and they are moving away when they are further apart each other. This distance indicate that this is weak field region. Okay. Now this is for a point positive charge. Okay. That means for point positive charge, what will be the shapes of equipotential surface? What will be the shape of equipotential surface? The shape of equipotential surfaces are nothing but the concentric spheres. The concentric spheres with increasing space between them. See, the space between them is less, increasing with space between them increasing as we move away from charge. That means as we move away from the charge, the space between the equipotential surfaces is continuously increasing, which shows that field is becoming weaker and weaker when we go away from the charge. Okay, this is about point charge. Then we will see how to draw the equipotential surfaces. See, once again, one more thing what we remember is, this is an equipotential surface, which means potential at all the points at this distance will be same. Potential at all the points on this surface will be same. Suppose that potential at each point on this surface is 10 volt. On this surface, equipotential surface means what? The potential on each point, potential at every point on this surface will be same. If same means it will be held to some fixed value. Suppose that it is 10 volt. At every point on this surface, potential is 10 volt. And if I consider the outermost surface, on this also potential will be same. Potential will be same, but it will not be 10 volt because we moved away from the charge. That means distance is increased. It may have some 6 potential, 6 volt, or suppose that it is 10 volt. Then next on the next surface, potential at each point will not be 10, it will be less than 10, again less than, suppose if it is 9, it is 10, 8, 7, 6 volt like that. Potential at each point on this surface will be same, but it is not equal to the potential at every point on this surface, because we moved away from the charge, potential goes on decreasing. That means in the direction of the field, if you go further away from the charge, potential goes on decreasing. Okay. This is the direction of the field. In this direction, potential decreases. If you go against field, potential increases. If you go in the direction of the field, potential decreases. Okay, this is about point charge. Then second case, for uniform field between two plates. If you have two plates here, one will be positively charged like this. There will be another plate which is negatively charged. An uniform field exists between these two plates. This will be minus, 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 minus. If I want to draw the equipotential surface here, see, this is the direction of electric field. Equipotential surface, I told you in one of the properties, second property what we discussed is, equipotential surface will be always perpendicular to the direction of electric field. See, if I want to draw an equipotential surface here, I will draw it like this. If I want to draw it here, this will be another equipotential surface. This will be another equipotential surface like this. These are the equipotential surfaces, which are nothing but equidistant parallel planes. These are the equidistant parallel planes. Like this. because field is uniform and everywhere field is uniform. If this is, suppose that if this is the direction of the field, I told you in the direction of the field potential goes on decreasing. That means on this surface, if every point has 10 volt, on this surface every point does not have 10 volt. That means potential goes on decreasing in the direction of the field. It will maybe 8 volt like this, it may be 6 volt like this. It means potential is decreasing in the direction of the field. Okay. This is 10 volt means every point on this surface will be having 10 volt. Every point on this surface will be having 8 volt. And all the points on this surface will be having 6 volt potential. All are having same potential, therefore it is called equipotential surface. It does not mean that all the surface should have same potential. On a particular surface, every point should have, suppose potential at one point is 10 volt, that means potential at all the points should be 10 volt. Okay, these are what are the shapes of these lines? This indicates the direction of electric field. These are equidistant parallel planes, equidistant parallel planes perpendicular to the field. This is for uniform field between two plates. Then if I want to draw it for dipole, system of two charges, equal and opposite charges separated by small distance. Now see, this is plus q. I will take it as like this, plus q, and this is negative charge. If I want to draw the equipotential surface, first let me draw the electric field lines. Electric field lines will be from, they start at positive charge and end at negative charge. These are the electric field lines moving away from the positive charge. 2, 3, 4, 5 lines. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 like this. This all will be going away from this charge. This charges will be moving towards this is 5. So they are moving towards this. Number of lines you should draw same on both sides. 2, 3, 4, 5. Moving towards. These are the electric field lines. Okay. Then how to draw the equipotential surface? It is a system of dipole. Positive and negative charges separated by small distance. See, to draw the equipotential surface, first let us see in which region field is strong and in which region field is weak. Suppose if I place a test charge here, or else if I take a point here, in between these 2 points, the electric field due to these 2 charges will be in the same direction or opposite direction. You say it first. At this point, if you place a point charge, this charge will repel it like this, and this charge will attract it like this. Electric field at this point will be away from the positive charge due to this charge, and due to this charge it will be towards its charge. That means in between, anywhere between these two charges, at all the points electric field is in the same direction. Electric field due to these two positive charges will be the same direction. That means if the fields are acting in the same direction, then the net field will be more. And in this point, at these points, if you see, in this point, the field due to this charge will be away like this. Positive charge field is away, and negative charge field is towards. That means field is towards the charge and field is away from the charge. See, the positive charge away, negative charge towards. That means in this region, outside the two charges, fields will be opposite in direction. If the fields are in the opposite direction, then net field will be less. That means this side and this side field is weaker. And in this region, since two fields are in the same direction, then the net field will be more. That means it is strong field region and it is weak field region. Try to understand this. Plus Q minus Q. In between this field due to this will be away and field due to this will be towards it. That means two fields are in the same direction. If two fields are in the same direction, then the net field will be more. That means net field will be more here. And in this direction, this field due to this charge will be away and field due to this charge will be towards. That means two fields are in the opposite direction. Therefore, field will be weaker here. Okay. Then I told you how equipotential surfaces can be drawn. When drawing the equipotential surfaces, I told you equipotential surfaces will be closer in the region of strong field and they will be further away, further apart in the region of weak field. So this side and this side we have weak field and in between we have strong field. See how to draw the equipotential surfaces. Strong field, they must be closer to each other. This is one point. I am taking it like this. This is another surface like this. See, this is another surface. Point charge it is. Point charge will be concentric circles only. We should draw concentric circles. See, 3 circles I have drawn. One more. This is fourth. This is the fourth circle. They are in this region, strong field is there. That means they must be close to each other. And in this region, strong field is there. They must be close. Outside these two charges when you go, see, observe it carefully. This will go here. See, this side the lines are closer to each other and this side they are away from each other, which indicates that this field is strong, this region is strong field region and this region is weak field region. This side also you should draw in the same manner. Should take them away from each other. They must be away from each other this side. This side they must be closer to each other. Okay. Then if I draw one more line like this, they will form circle like this. They will form a closed loop like this. That means for a system of unlike charges in between region, if electric fields, see, anywhere in between these two charges, electric field is strong. This indicate that this region is strong field region where lines are closer, and here lines are further apart from each other. This indicates that this is weak field region. This is strong field region.